The mosasaurs are an extinct family of marine lizards that evolved in the age of dinosaurs. They underwent a remarkable evolutionary diversification event until by the end of the Cretaceous period, mosasaurs evolved a huge range of species to eat a huge range of prey: fish, squid, crustaceans, mollusks, and one mosasaur evolved that ate all the other mosasaurs. This talk is about that mosasaur, an extraordinary creature, an apex predator called Thalassotitan atrox, a giant carnivorous mosasaur from the late Cretaceous of Africa. Mosasaurs, once again, are lizards. They're not dinosaurs. They're related to modern things like iguanas, varanid lizards, snakes, not to the dinosaurs. They were huge marine lizards. They're up to 12 or 15 meters long. They're highly adapted for life in water, just like whales. Imagine a Komodo dragon, but it has flippers instead of legs and with a shark-like tail. And that's more or less what a mosasaur was. Thalassotitan was one of the most highly specialized and among the last of the mosasaurs. It was a giant 9-meter-long mosasaur from the very end of the Maastrichtian period. It lived around 66 million years ago, along with the last dinosaurs, things like T-Rex and Triceratops. It was one of the last animals on Earth from the Cretaceous period of the mosasaurs, and then went extinct at the KPG boundary along with the last dinosaurs. And it appears to have been an apex predator similar to modern orcas and great whites. That is, it's not eating little fish, it's eating other large marine tetrapods. Whereas orcas today eat things like seals and sea lions and whales, mosasaurs would have eaten the marine reptiles that dominated the day, things like mosasaurs and plesiosaurs. Its evolution tells us something really interesting, I think, about the marine ecosystem of the time. Just before the Chicxulub asteroid impact that wiped out the dinosaurs and the mosasaurs, and it suggests that there's a very highly diverse and healthy marine ecosystem in a sudden extinction at this time period. I'm also going to argue, however, that this animal shows us some really interesting things about late Cretaceous evolutionary dynamics. And in particular, there's some remarkable evolutionary parallels to the tyrannosaurs as well as to other dinosaurs. And what this implies is a common evolutionary driver that's driving the radiation of mosasaurs in the seas and the radiation of dinosaurs on land in the final 25 million years of the Cretaceous. So back at the very end of the Cretaceous period, the sea levels are a lot higher than they are today. This isn't primarily the result of the warmer climate, so it was a lot warmer back then. It's caused by volcanic activity. We have huge volcanoes that are built up on the seafloor as a result of seafloor spreading, and the formation of these vast undersea mountain chains shoves water out of the way, and it shoves that water, it has to go somewhere, and it goes up onto the continents. And in North Africa, the Atlantic floods Morocco as far as the Atlas Mountains, and most of the Sahara Desert was underwater, so you could have basically taken a boat across the Sahara. What this means for us today is that North Africa is a remarkable place to look for marine vertebrates, because this is all underwater. So you go out there and what you find are lots and lots and lots of marine reptiles from the end of the age of dinosaurs. So today these are developed over much of North Africa and into the Middle East as phosphate deposits. These are these huge marine beds. They cover huge areas of Morocco, North Africa, and they span the Cretaceous-Paleogene boundary, that is the very end of the Cretaceous period and the transition to the Cenozoic, the end of the Maastrichtian at 66 million years ago. And in Morocco, these run up to the PETM, the Paleocene-Eocene thermal maximum, at the end of the Paleocene, the start of the Eocene, this big hyperthermal event, and then on into the early Eocene around 50 million years ago. So what this means is that we have a remarkable record of the Cretaceous-Paleogene transition. We can see what the marine vertebrate fauna is doing in the kind of the twilight of the Cretaceous and the very start of the Cenozoic. We have a snapshot of the world as it was just before the asteroid changed everything, before the asteroid hits, causes vast mass extinction, wipes these things out. We can see this twilight of the dinosaurs and twilight of the mosasaurs, this era at the very, very end of the Cretaceous period. And then we have about 15 million years of recovery, and we can see the world trying to rebuild. So the equivalent in terrestrial ecosystems would be the Cretaceous Hell Creek Formation and its Paleocene formations after that in Western North America. And what that tells us about terrestrial ecosystems, the phosphates of Morocco are telling us about marine ecosystems and the transition across this, one of the biggest mass extinction events in Earth's history. So why is this such a rich area? Well, then as now, the trade winds drove to the west. The Coriolis force causes the trade winds, and the trade winds are pushing off the coast towards the west. And what this means is pushing the water, the surface waters are flowing off to the west. It's driving these currents. So these waters flow off, something has to replace them. And what happens is the surface waters flow off to the west and bottom waters come up. There's an upwelling zone, an upwelling of bottom waters. And these waters are really rich in nutrients. They're full of things like phosphorus, they're full of iron, and these nutrients are otherwise rare in the ocean. They limit the ability of organisms like phytoplankton to grow. There's just not enough. It's kind of, it's sort of a nutrient desert throughout most of the ocean. There just isn't enough phosphorus, isn't enough iron out there for things to grow. So when these things come up from the bottom waters, it fertilizes the ocean and creates this massive phytoplankton bloom. In addition to having all these nutrients, we're at fairly low latitudes, there's fairly intense sunlight. So we have these phytoplankton blooms. The phytoplankton feeds zooplankton. The zooplankton feeds little crustaceans and small fish. These feed bigger fish and squid. And these feed things like mosasaurs, plesiosaurs, and sea turtles. So this incredibly productive marine ecosystem has this, just all this productivity is feeding this elaborate, diverse food chain, all these marine reptiles, all these fish, all these sharks up on top of it. And then what happens is all these creatures die and the remains rain down to the seafloor, and it creates these vast bone beds. I've never seen bone beds like this anywhere on Earth. You have mosasaur skeletons every few meters or 10 meters or something like that, scattered with fish bones and mosasaur teeth and all these things. And these beds go on for kilometers, vast bone beds. And we have associated remains, sometimes articular remains, a lot of isolated stuff. And then the matrix itself is actually fossil. This is pretty insane. If you prep this stuff out with a needle and you look at it on the dissecting scope, what you'll see is that what looks like little sand grains, and technically they are sand grains, they're sand-sized particles, they're little tiny bits of fish bone and fish teeth. So it's fossils preserved in a fossil matrix, which is pretty crazy when you think about it. And it's also maddening if you try to CT scan the stuff, because it's bone inside bone. It's all got the same density. So it doesn't CT scan super well, but it's just incredibly rich, and it's the result of this marine upwelling zone. And then today, these phosphate sands are mined for fertilizer. Basically, we have this ancient Cretaceous bone meal, which is used to fertilize fields. And in the process, these strip mines expose these beds and have exposed and produced this extraordinary marine vertebrate fauna, maybe the most diverse Mesozoic marine vertebrate fauna known. So we have this extraordinarily rich record of marine reptiles from the final million years of the Cretaceous, from the phosphates. We have sharks, we have fish, we have sea turtles, we have plesiosaurs. And the mosasaurs are exceptionally diverse, and we're still rapidly finding new species. It seems possible there may have been as many as 20 or 30 species in the fauna. And this might sound kind of crazy, but there's something like 25 dinosaur species in the Hell Creek. So it's not crazy to think there could have been 25 or 30 mosasaurs. And the most diverse whale faunas have something like over 30 and almost 40 species in the coasts of South Africa, for example. So if you can have something like 39 cetacean species in one area, why couldn't you have 30 or 40 mosasaur species? So these things seem to be really extraordinarily diverse, and basically nowhere else on Earth do we have a record of a Maastrichtian marine fauna that's even approaches this level of diversity. So Morocco, even before we started working there, already had the world's most diverse mosasaur faunas, but we've kept finding new species in recent years. One of these species is this creature called xenodons. It's this really bizarre little mosasaur, and it has these small blade-like teeth, like little razor blades, packed together to create this serrated cutting surface. It's not like any mosasaur we've ever seen before. It's not like any other lizard we've seen before. It's not like any other tetrapod. So we're just seeing some really, really bizarre things here. Another new species that's turned up in recent years is this creature called pleurodons. It has these very long jaws with these hooked teeth, so we gave it the name Pleurodons serpentis. And it has small eyes, so probably not very visually oriented. Maybe it's hunting at night or at depth where there's not a lot of light, but it has all these nerve openings in the snouts. It's probably a tactile hunter of some sort. Maybe hunting at night in shallow waters, in the reefs, or maybe hunting in deep waters using tactile foraging. It's doing something weird, another new species. And even more mosasaurs. There's this creature called stellodons, known from just a single partial jaw. There's a lot of rare species in the fauna, and it has these really bizarre teeth. They have multiple blades, these carinae, anywhere from 4 to 6 of these. So the teeth look sometimes some look like a Phillips head screwdriver with 4 edges on them. Some look like a hex wrench. It's doing something very, very bizarre. So we already had a really diverse fauna. We keep finding new species. And one of the most extraordinary species to emerge out of the fauna in recent years has been this guy. So this is Thalassotitan atrox, a giant predatory mosasaur. It's one of the most common species, and yet it had remained undescribed until we described it a few years ago, even though it is one of the most common, if not the most common animals in the assemblage. So what exactly is this creature? It's very similar to a creature called Prognathodon. However, it's much bigger, it has more robust jaws, more specialized teeth. It's highly adapted for an apex predator role. And it is a really extraordinary window into the diversity of this fauna and just understanding the ecosystem that existed back then and the evolution of the mosasaurs. So we have some really good material of this animal. Over the years, we've been able to acquire some really extraordinary specimens from the museum in Marrakesh. And the type consists of one of the best mosasaur skulls I've ever seen. It's a virtually complete skull, lower jaws, part of the spine, and it's really beautiful. It's very well prepared, and it's really a spectacular specimen. And okay, it's a little bit crushed, but you probably wouldn't look as good after 66 million years. So this is really a nice specimen and gives us a beautiful picture of what this animal is. And this was the holotype. We also, however, have a lot of other specimens. We have numerous skulls, we have partial skeletons, we have flippers, we have tails, and we have a nearly complete articulated skeleton that turned up a couple of years ago. So this is kind of an impressive animal, and hopefully we can get this on display in a museum someday so people can go and see it, because they're really remarkable and really beautiful animals. The most distinctive bones in the mosasaur are typically the frontals and the parietals. So a lot of mosasaurs have very similar teeth, very similar jaws, but then you get into the details of skull bones, how the shape of the skull bones, how they knit together and articulate with other skull bones. And the devil is in these details, and it helps you discriminate these different species. So our animal is distinguished by a very short, broad frontal, which is constricted to the front. And this distinguishes it from a very similar looking animal called Prognathodon saturator, which has a longer frontal. Prognathodon also has slightly longer teeth, but that's a very more subtle feature. These are kind of very obvious features. They're consistent. We've seen this in multiple specimens. These are a different species. It's not saturator. It's something larger, more specialized. It actually, in certain features, like the very short, broad frontal, looks a little more like Prognathodon currii. But currii has these very straight, blunt teeth, which this thing lacks. And these subtle differences tell us that we have a new species in the phosphates that hadn't previously been described anywhere else in the world. We did a phylogenetic analysis. Tells us that it's a part of this Prognathodontan mosasaurs. This is things like various species of Prognathodon, and then our new species Thalassotitan. And its closest relatives are things like Prognathodon saturator and Prognathodon currii from Israel. And these are these giant mosasaurs. They're getting about 9 or 10 meters long. So there seems to be a single evolution of gigantism within this clade. And then these things are part of a broader radiation of Prognathodon-like mosasaurs occurring in the Campanian and the Maastrichtian. So we have this new species, and it's fun to describe new species and figure out the relationships, but another really interesting thing is understanding their biology. How did this animal live? What was its lifestyle like? And we have a huge amount of evidence available here. We have the jaw structure, we have the tooth structure, we have the tooth wear, the gut contents, and what this repeatedly tells us is that this animal is an apex predator. It is the top of the marine food chain, just like orcas and just like white sharks. It's not eating little fish, it's eating other marine tetrapods the same way a killer whale would eat whales. So this is a top predator, and there's a number of different lines of evidence that independently tell us this and kind of converge on this explanation. So first of all, just the structure of the jaws and the skull. Most mosasaurs have relatively long, slender jaws. By having long jaws, they can close quite quickly. It's good for seizing fast-moving fish. They don't need to be very deep or robust because, the bite is quite weak and the prey isn't that strong. It doesn't need a high bite force to subdue these things. The Thalassotitan is built very differently. It has these very short, deep jaws. And the short jaws, like a bulldog, give it a lot of leverage, a very powerful bite. And the deep jaws give it a high bending resistance so that it can exert very high bite forces and withstand very high bite forces when it's biting large prey. So it's adapted to a very powerful bite, not a fast bite, and a very forceful bite. And this allows it to subdue large animals. The skull is also very unusual in shape for a mosasaur. It's extremely short and extremely broad, and it looks like a killer whale. Killer whales have this similarly short, broad snout. I'm not exactly sure what the biomechanics are, but there seems to be a form-function correlation of having this very short, broad snout. You see something similar in alligators, and it's useful for tearing apart prey items, it seems. Just having a very short, broad, strong snout, these things could bite large animals and tear off chunks of food. Now, one important difference between this animal and a killer whale, however, which makes it in some ways a more formidable predator, is it has an intramandibular joint. The killer whale has a single bone, the dentary, making up the entire lower jaw. So the jaw can hinge, open, and close, but it can't really flex. The mosasaur has several different bones making up the lower jaw and has a hinge halfway down the jaw. And what that means is the jaws can kind of flex out to the side and expand the gape. And this is similar to what you'll see in snakes and in monitor lizards, and it allows them to expand the gape of the head. So the skull is about 50 centimeters wide, and it could have expanded its jaws, so it could have swallowed things much wider than that. I mean, maybe even close to a meter in diameter. So it could swallow very, very large prey items whole. So it could basically attack with these powerful jaws, attack prey items, grab them, tear them apart, and then swallow the pieces. The teeth are really, really interesting, and this is kind of what gave me this idea that we had some sort of orca-style top predator. So if you look at the teeth of something like a Mosasaurus, they're good for fish eating and piercing and holding fish. They're quite tall and slender, and again, kind of for stabbing into prey and holding it. And actually, some killer whales actually look like this. There is a group of killer whales that are residents of the Pacific Northwest, and they kind of hang out near river mouths, and they eat salmon all the time. So they don't need really powerful teeth because they're just eating fish. The Thalassotitan doesn't look like this. The Thalassotitan doesn't look like fish-eating mosasaurs or fish-eating orcas. It has these really short, massive, conical, slightly recurved teeth, and they look like the teeth of transient orcas. And transient orcas are specialists on marine mammals. They live offshore, they roam around huge areas to find marine mammal prey, and they will attack and kill marine mammals. They will grab and tear apart things like sea lions, even whales. So the Thalassotitan, it doesn't just look like an orca. It looks specifically like the orcas that eat sea lions and whales. It has the teeth of a predator that is designed to attack and tear apart other large marine animals. Another more direct line of evidence, direct evidence of how these things behaved, of their diet, is tooth wear. And the Thalassotitan teeth show incredibly heavy wear and breakage. I've never seen an animal that has this level of tooth wear. They have really bad teeth. Even compared to something like a T-Rex, which is chomping into bone, it has much more heavier damage to the teeth than T-Rex does. So what we're seeing is the teeth are broken, they're chipped, they're worn, they're ground down, and all of this suggests really forceful tooth-to-bone contact. It's not eating fish with these little delicate bones, these little flexible, delicate bones. It is eating large marine reptiles and breaking and chipping its teeth on them. Things like other mosasaurs, things like plesiosaurs, and things like sea turtles. And the force exerted against the bone is causing all this damage. Here's another specimen that shows the incredibly extensive wear, blunting, and breakage of these teeth. Now, one thing you have to keep in mind is that there's relatively fast tooth replacement in mosasaurs. They shed and regrew them throughout life like sharks, maybe not quite as rapidly as sharks, but for comparison, monitor lizards like Komodo dragons would replace their teeth every few months. So what this means is this heavy damage we're seeing is occurring in a really short period of time, maybe just a few months. We're seeing weeks and months of wear here, not a lifetime of use, and yet we're seeing really, really heavy tooth wear. And that makes this tooth wear all the more impressive. It's just a really high level of abuse of these teeth and use of basically tooth on bone contact is causing this. Indirect evidence also comes from other fossils we find in the phosphates. One of the really curious features I noted about the phosphates as I started going through all these specimens is that a lot of these specimens weren't very well preserved. Typically, if you get a shed tooth from the phosphate, it's covered by dense, shiny enamel. That's true if it's a fish tooth or a mosasaur tooth or a plesiosaur tooth. And this is typically true of teeth and skulls and jaws. Like this Pleurodons here has these nice, pretty, shiny teeth. They look really beautiful. But a number of specimens, you have this otherwise pretty well-preserved specimen, you look at the teeth, and I was like, well, what's going on here? The enamel is gone, and so is a lot of the dentine, and the teeth are kind of worn down to these little like nubs. And the teeth appear to have suffered acid damage. The tooth mineral has just been dissolved away. Well, how would that happen? Now, you could invoke some sort of scenario where the tooth dissolution is happening on the seafloor or maybe in the sediments after burial. But if this is the case, it's unclear why it would only hit some specimens. And it's never the case that the shed teeth are ever dissolved, only the ones that are in jaws. So what I think is actually going on here is these represent digested remains. These jaws of mosasaurs and fish represent skulls that have been ingested, partly dissolved in stomach acid. And the stomach acid preferentially attacks the enamel and the dentine of the teeth because it's exposed, whereas like the bones of the jaws are behind skin under muscle, can protect a bit from the acids. And also all the collagenous matrix of the jaws helps protect them from stomach acids. So the teeth are being hit first and hardest and dissolved away, being highly mineralized by the stomach acids. And then once these things are partially digested and the muscle and the flesh has come off, the bones are vomited up. And so basically what we're seeing is mosasaur vomit. We've seen this acid damage in dozens of specimens representing many different species of mosasaurs. So we've seen it in Gavialamimus, we've seen it in Halosaurus, we've seen it in Arameosaurus. So at least 3 different mosasaur taxa show this damage. So it's hitting a huge range of different mosasaurs, including some pretty large animals. This Arameosaurus might have been something like 4 or 5 meters long. And it, or at least the head, was ingested, digested, and then vomited up. Curiously, we have one specimen. It's a turtle shell found in association with the jaw elements of this saber-toothed fish called Encotis. And the Encotis teeth have their enamel stripped away. So they appear to have been digested by a mosasaur. And what I'm going to argue is the association of the turtle and the fish. The jaws are directly on top of the turtle skull and kind of mixed in with turtle bones. This is unlikely to be coincidence. I think what we're seeing here is a gastric pellet. This is a clump of bones, both fish bones and turtle bones, that were ingested by a mosasaur and then vomited up, and they kind of rained down to the seafloor together. Maybe the most astonishing example of this is this specimen. This is the 50 centimeter long skull of a plesiosaur, a half-meter long skull, and the bones have been shattered and the enamel partially dissolved off the teeth. And what it looks like is that this animal had its head bitten off, digested, and then vomited up. And so we're seeing a plesiosaur that had its head bit off by a mosasaur. Now, obviously we can't be 100% certain what species ate these animals, but we can guess. We have a marine predator. We have these marine reptiles, and they're being eaten and digested by a large marine predator. And in the same fauna, we have a very common large predatory mosasaur that is adapted to eat large marine animals and marine reptiles. And as tooth wear suggested, it ate large marine reptiles. And then meanwhile, the other mosasaurs, things like Mosasaurus, seem to be deep diving fish specialists, probably wouldn't do this very often. Given that we have a specialist predator of marine tetrapods, the most likely culprit is Thalassotitan. I can't prove it, but the circumstantial evidence is pretty strong that Thalassotitan is responsible for many, most, maybe all of these vomited remains and killed these animals and ate them. This is a new specimen where we can be a little bit more certain about the assignment because what we have here, it's a little hard to see in kind of the mess of the rib cage, but inside this mess of bone is the limb bone of a baby plesiosaur. It appears to have been the last meal of Thalassotitan. So here we have some direct evidence of prey preference showing that Thalassotitan did in fact eat marine reptiles, and in particular young plesiosaurs. They're not eating fish exclusively, or maybe not even primarily, they're eating other marine reptiles. So there's a lot of other interesting things about this animal. There's still a lot to learn about it, about its biology. Another piece of evidence that these are really ferocious animals, if you didn't need more evidence, is evidence for combat in these things. We have an incredibly high frequency of injury in large Thalassotitan individuals. We frequently see these bony pits and calluses that represent partially healed bite marks from other mosasaurs. So like modern sperm whales, these things may have fought over feeding territories and over access to mates. So what do we have? We have a new species of giant predatory mosasaur. It's a pretty cool animal in and of itself. The biology is really, really fascinating, but what are the evolutionary implications? Well, Thalassotitan is this extraordinary apex predator. It has these tearing teeth, these powerful jaws, a big broad skull to crush and tear apart prey. It's an apex predator, the T-Rex of the seas. And what does it tell us that mosasaurs are moving into this niche? And about not just mosasaurs, but Cretaceous ecosystems more broadly. Well, first of all, what we're seeing is extraordinary high diversity of mosasaurs in late Maastrichtian and Morocco. Between Thalassotitan, new things like xenodons and stellidans and Pleurodon serpentis, and all these species we still need to describe, I would guess there's something like 25 to 30 species, conservatively, in the uppermost part of the phosphates. The issue is here that as in most ecosystems, as in modern ecosystems, most species are rare. Most ecosystems have a handful of common species and a lot of rare things. So what's happening is we found most of the common things, things like Mosasaurus bojae, things like Thalassotitan, things like Halosaurus ehrenborgi, and now slowly we're finding and naming the rare ones. And some of these are known from just a single skull or a single jaw, but we're starting to flesh out the diversity. And what we're finding is that once we've discovered the common things and described them, there's still a lot of work left to do on the rare things. So how is this diversity achieved? Well, we have very high functional diversity. That means they're doing a lot of different things. They're in different ecological niches. Now, in certain groups, like say duck-billed dinosaurs or ceratopsians, we have a lot of species, but they differ mostly in subtle details. The crest, the teeth are fairly similar, the beaks are fairly similar. They probably had fairly similar niches and diets, and that's not what we're seeing in mosasaurs. We are seeing extraordinary variety of jaw shapes and tooth shapes and skull shapes, and this implies different diets, different foraging strategies, different ways of processing their prey. So they're eating a lot of different things, they're hunting in different ways. We also see other differences that relate to how they would hunt. Some have huge eyes, they're clearly very visually oriented. Some have small eyes, relying on other senses. Some have different body shapes, different flipper shapes. Some obviously are huge, some are a few meters long, some of these things are 12 to 15 meters long. So this is really extraordinary. No other marine reptile group seems to be this diverse. It's not really entirely clear if this reflects the underlying diversity of their prey items or if they're just better at specializing. The fact that plesiosaurs don't show this, they basically all have kind of in this ecosystem the same basic body plan, the same basic teeth. They have long skinny necks, little heads with kind of pointy pencil-shaped teeth. That implies to me that the mosasaurs are somehow better at specializing than plesiosaurs were. They're just able to evolve a wider range of jaw shapes and tooth shapes that allows them to prey on a wider range of things. So this tells us, Thalassotitan and everything else, your Thalassotitan and xenodons and Pleurodons and all these crazy mosasaurs. What this tells us is this is a very diverse group doing a huge range of different things, occupying different niches, feeding on different things, and they're increasing the diversity as they approach the Cretaceous-Paleogene boundary. As they go up towards 66 million years, they're becoming more diverse and more specialized. This is not a group in decline, and this strongly favors a catastrophic explanation for the extinction. I think long-term climate change, competition with other groups, probably had little or nothing to do with their extinction. This is a group that would have done perfectly well if the asteroid had deviated by even just, a fraction of a degree. It would have missed the Earth. The mosasaurs would have kept on diversifying and evolving, probably for 66 million years, and they'd still be here. They were highly successful, the most successful they'd ever been, maybe the most successful group of marine reptiles ever, and then suddenly they vanished when that asteroid hit, and that's not a coincidence. This is a group that was cut down in its prime, not one that was suffering a slow decline. And again, almost certainly without the asteroid, they'd probably still be here today. So the other thing that's really striking about Thalassotitan in particular, and also to a degree mosasaurs in general, is the way the evolution of the mosasaurs here is paralleling what we see in dinosaurs. So Thalassotitan, in terms of its large size, its big skull, robust teeth, its crushing jaws, we've seen this all before in Tyrannosaurus. It's kind of the marine equivalent of T-Rex, this thing designed to attack and crush and tear apart large prey items. And what's more interesting, beyond just the convergence and function, is the evolutionary dynamic is quite similar. So we have this pattern in which there is a mid-Cretaceous extinction of marine apex predators. The giant pliosaurs go extinct. Mosasaurs move into that niche, become very large, very specialized, and become specialized apex predators. And we have basically the exact same thing happening at the same time on land. we have these apex predators, the dinosaurs. They go extinct in the middle of the Cretaceous, sometime in the end of the Cenomanian or maybe the middle of the Trionian. They get wiped out. These giant multi-ton predators vanish. Tyrannosaurs move into that niche, get bigger and bigger. We have the appearance of these giant tyrannosaurs, things like Tyrannosaurus and Tarbosaurus. So the fact that marine and terrestrial groups are showing similar patterns at the same time is a strong indicator that there's some kind of common driver for the evolution of both the marine and the terrestrial ecosystems. And it's not just the tyrannosaurs that are radiating. We see multiple dinosaur clades that are doing this at the same time. The duckbill stage of major radiation, so the ceratopsians, so the titanosaurs. And it's not just dinosaurs either. We see major radiations of varanoid lizards, of iguanian lizards, placental mammals. Even birds are radiating at this time. The last 25 million years of the Cretaceous, after the Cenomanian-Turonian transition, there's this period of phenomenal evolutionary innovation, of which mosasaurs are one example, tyrannosaurs are another. All these other dinosaur, lizard, mammal, and bird groups are radiating at the same time. And what this suggests is a common evolutionary driver in multiple ecosystems, marine, terrestrial, hitting multiple groups all at the same time. We also see this in terms of the size evolution. Mosasaurs are all getting big at the same time. Multiple different groups of dinosaurs getting big at the same time. Things like hadrosaurs, ceratopsids, tyrannosaurs are all increasing in size as you go into the Campanian Maastrichtian. Even among mammals, I mean, mammals don't get super huge in the Cretaceous, obviously, but like the biggest placentals and the biggest multituberculates are occurring at the end of the Cretaceous period alongside your biggest mosasaurs and your biggest tyrannosaurs. And the biggest ornithurine birds and antiornithine birds we've ever seen appear at this time period too. We're seeing large varanoid lizards and polyglophanodontid lizards. So we're seeing a size increase in multiple groups in this final 25 million years of the Cretaceous at the same time they're diversifying. So what's driving all of this? Well, first of all, I'd argue that the fact we see similarities in the evolution of marine and terrestrial ecosystems suggests that the drivers cannot be specific to either. You can't invoke a driver that's specific to terrestrial ecosystems. Like, oh, well, clearly it's angiosperms. Okay, well, angiosperms might explain dinosaurs and mammals. It doesn't explain why mosasaurs are diversifying. That doesn't make any sense. Likewise, you can't use a marine-specific event to explain this overall pattern. Like, clearly it's marine productivity. Okay, well, that might explain mosasaurs, but high marine productivity wouldn't explain why tyrannosaurs are doing the exact same thing. So angiosperms works for one, marine productivity works for one, but what we need is an explanation that explains both. And that explains some broader environmental shift. Long-term climate change might do it. There's a cooling event. The problem with that, though, is that we're seeing warm-blooded and cold-blooded things kind of do the same thing. So I could see cooling explain why dinosaurs and mammals, which are warm-blooded, would get bigger. But why would cooling explain why the lizards and snakes get bigger at the end? That doesn't make any sense. So I think something else has got to be going on here. What I'm going to argue is that historically, when you see adaptive radiation, and with that size increase, this is a classic signal of recovery from a mass extinction. So remember, the end Cretaceous mass extinction happens. We have little mammals, little birds. They diversify and they get big. That's the signal of a recovery from mass extinction. So we're seeing as multiple groups diversifying and getting big in the final 25 million years. What this implies to me is there was a recovery from an extinction event in the middle of Cretaceous. So what might be driving this? Well, there's a major event called the Bonarelli event. It's associated with the Oceanic Anorexic Event 2, caused by volcanic eruption. And this is causing a brief warming spike and then a cooling spike. And maybe this warming and cooling pulse is causing a lot of species to go extinct. And a lot of things seem to go out at this time. We see ichthyosaurs and giant plesiosaurs, giant carcharodontosaurs, spinosaurs. These things are not known after OAE2 and the Cenomanian-Turonian boundary. So this may have wiped out a bunch of things. A number of other species may persist into the Turonian for a while, some of the smaller carcharodontosaurs, some of the small plesiosaurs. So it may have been a pulsed extinction. And there is also another event in the Turonian. It's called, it's the Cretaceous thermal maximum. So it gets really hot, and the climate comes down, and it gets hot again. And so this kind of warming, cooling, warming pulse, there might have been a series of climate change events that are causing this turnover event. So this might have caused a series of extinctions of things like plesiosaurs in the oceans, things like carcharodontosaurs on land. Sauropods go out at this time period in North America, at least. And some of the small sauropods like Urbachosaurs disappear from Gondwana. And maybe these extinction events, by wiping out marine reptiles, by wiping out dinosaurs and other species, are allowing the survivors to radiate and get big in the Cretaceous. And that's why we're seeing mosasaurs and tyrannosaurs basically evolving in the exact same way. So big predators are, of course, intrinsically interesting. Why should we say things like Thalassotitan? Well, they're pretty cool. They're pretty amazing. I mean, this is an animal that just would like kill and tear apart and eat anything that ran into the ocean. That is intrinsically fascinating. But I think there's actually getting beyond that. Just kind of like, there's some really interesting macroevolutionary problems wrapped up in the evolution of predators. Top predators are just one part of the ecosystem. They're a small part of biomass. They're a small part of diversity, but they reflect the lower levels of the food chain. The productivity of that food chain, the diversity of the prey items, all of these things are going to reflect themselves in terms of what type of predators evolve. And I'm going to argue that these giant predators are like indicator species. When giant predators evolve, that tells you there's a very highly productive, diverse ecosystem to feed these things. There's got to be a lot of feed to have these big things in the sea. And the same is true on land. There's got to be a lot of things to eat for something like T-Rex to evolve. And then when these things disappear, that's telling you something as well. And the disappearance and turnover of megapredators is maybe the single best indicator of mass extinction events. They're kind of like the canary in the coal mine, so to speak. When your apex predators go out, that's a strong signal of mass extinction. So the extinction of mosasaurs at the end of the Cretaceous and the evolution of sharks and whales afterwards reflects this major mass extinction event, the end Cretaceous mass extinction event. In the same way, the evolution of the giant mosasaurs in the first place and the way it parallels the evolution of the tyrannosaurs may tell us something really, really significant is happening in the middle of Cretaceous, that there is this major extinction event that's been underappreciated, and mosasaurs and tyrannosaurs are part of the recovery and the radiations following this mass extinction event. So a parting thought, it's all connected. It's really easy to get lost in one little area of science, and it can be a little bit of fun too. You can spend your whole career on one family, like the mosasaurs, or even one subgroup of mosasaurs, and get to know it really, really in detail. You could spend your whole career focused on just one species, like T-Rex, or maybe your whole career is just focused on Neanderthals. And you can come to know that group or that species in great depth, and there's a lot of value to that. But your knowledge becomes very, very deep, but very, very narrow. And the problem is you then lack the breadth of knowledge to see how your species fits in with all the others. And I've been lucky to work across a number of different groups. I've worked on birds, I've worked on ceratopsians, I've worked on tyrannosaurs, lizards, snakes, mosasaurs. And while that might mean I don't have the exhaustive knowledge that comes from specialization, I might not know every single bone of the T-Rex in great detail, it's given me the ability to look and see connections between things that don't initially seem connected. So I didn't initially set out to study mosasaurs. There just seemed to be a lot of them available in Morocco. Seemed like a great opportunity. But in the process of getting in there and studying the mosasaurs and learning this group in detail, I started noticing all these interesting parallels with dinosaurs. And so I think that what that kind of tells us is that everything we study is all part of one big story. It's the story of how the world came to be. And every bone is a fossil of a species that was part of that story. And no matter how small that bone is, or no matter how obscure that species is, it has something to tell us about this bigger story, this history of life, if we're willing to listen.